this next video, we are going to look at methods for finding limits, and we're going to focus on the analytic method. Now, in the past videos, we talked about both the graphical and numeric methods, which in one case you had to look at the graph to figure out what the y values were doing as your x values approached a specific point. And for the numeric method, you were approximating the limit by looking at what the function value does numerically. In this case, we're going to do less of kind of an approximation and more of a direct method for solving for your limits. Now, in some cases, you're not going to be able to solve directly, and so we'll look at some of the algebraic techniques that will help get that analytic method found. So here, we're going to start with a few necessary conditions. So we're going to let c be a constant. We're going to let a and b be real numbers. N is going to be a positive integer. F and g are going to be functions, and we need the limit as x goes to a of both f and g to exist. And so what we're going to look at first are what we consider the limit laws. These are kind of like properties of real numbers, except now we're going to have specific properties for limits. So the first property says that if I take the limit as x goes to a of f of x plus g of x, or in other words, the limit of a sum of two functions, this is going to be equivalent to the limit as x goes to a of f of x plus the limit as x goes to a of g of x, or it's the sum of the limits. So the limit of the sum is the sum of the limits. Likewise, we have the same thing for subtraction. The limit as x goes to a of f of x minus g of x is going to be the limit as x goes to a of f of x minus the limit as x goes to a of g of x. So there's our two basic operations, addition and subtraction. And then we have multiplication. But unlike with real numbers, we have two different types of multiplication. We have a multiplication of limits, but then we also have what we call scalar multiplication. And this is where a constant comes in. If I have a limit as x goes to a of some constant times my function, then what this tells me I can do, or at least this limit law, it says that I can pull this constant out front and then look at the limit of the function. Okay, so that's our scalar multiplication. The other type, again, is our limits of multiplication of functions. So a lot like our sum and difference, if I take the limit as x goes to a of an f of x times a g of x, I'm going to get the limit as x goes to a of f of x times the limit as x goes to a of g of x. Our last basic operation is division. So if I look at the limit as x goes to a of an f of x over a g of x, and again here remember we're assuming both of these limits exist, but it didn't say what they had to be. So here we've got to be a little careful. This is going to equal the limit as x goes to a of f of x over the limit as x goes to a of g of x, but only if the limit as x goes to a of g of x does not equal 0. Okay? And that's one you have to actually be a little careful of, because sometimes you will get functions that it looks like I can do this operation, but then when you actually look at the value of the limit of g, it does go to 0. Okay? Our next properties are the ones that are going to give us the ability to find limits of all of our polynomial functions. So like we did when we were looking at the graphical and numerical, I want to be able to find things, limits of quadratics and cubics and fourth degree and things like that. And so we have some of those properties. We have the sums and differences, and we've got scalar multiplication, but then we also need things like the limit of a power or a limit of a constant. And so we need to take those into account as well. So the first is the limit as x goes to a of f of x to the n. So if I've got a function, I'm going to put brackets here so that you can see which piece I'm looking at. If I've got a function raised to a power, again, a positive integer power, so I'm thinking like polynomials, x squared, x cubed, x to the fourth, etc., then the limit is going to be the same as if I took the limit as x goes to a of f of x and then raised that value to the nth power. Okay? And then, like I said, the other nice one is for constants. So if I'm looking at polynomials, I can have something like 4x plus 2, where 2 is just a constant, and I need to be able to deal with that when I'm taking the limit. And so if I look at the limit as x goes to a of c, where c is some constant, this turns out to just be c. And that one is kind of hard to wrap your head around unless you think of it graphically. Okay? If I think of the graph of f of x equals c, it's just a horizontal line. And so if I look at the limit coming in from the left or right at any point along the curve, it's always going to be that value. Okay. Likewise with polynomials, we also get our linear function. And this one, again, you can kind of think of graphically. If I think of the graph y equals x, then for any point that I pick, the y value is going to be the same as the x value. Okay? So the limit as x goes to a of x is just going to be a, whatever that value I'm approaching is. Okay? And now we can combine some of these properties to create some more. So for example, if I look at property 8 and property 6, and I combine these, it says that if I look at the limit as x goes to a of x to the n, this is just going to be a to the n. Okay, so the x will give me the value of a, but then raising it to the nth power just means I'm raising a to the nth power. The same works for roots. So if I look at the limit as x goes to a of the nth root of x, here I can call this the nth root of the limit as x goes to a of x. Okay. Now this one will only work if n is even and a is positive. So we need the a to be greater than 0, and we need the n to be even, and that's because that's when our root is going to give us a real valued answer. And again, we can extend this a little bit further using properties 10 and property 6. Says that the limit as x approaches a of the nth root of f of x, meaning if it's not just x, the variable, it's some actual function, then I can still take the nth root of the limit as x goes to a of f of x. Okay, and again, this is for n even and a positive. So now let's use those limit laws to actually evaluate some limits. We'll start with the limit as x goes to 2 of 4x squared minus 7x plus 9. Okay, and so the first thing we can do is, when we look at this, is from our very first limit laws, we can separate this into sums and differences of limits. So here I can say this is the limit as x approaches 2 of 4x squared minus the limit as x approaches 2 of 7x plus the limit as x approaches 2 of 9. And this again comes from our first and second properties. Okay. From there, I can pull out those coefficients. So the 4 here I can bring out front. The 7 here I can bring out front. And this one's just going to stay as it is. And again, we can do this because of property 3. This was the one that said if I look at c times an f of x, I can pull that c out front. That's the scalar multiplication. Next, I can use my property 6 to bring out the exponent from my x squared term. Okay, and again, this was property 6. Okay, and then from there, I can use properties 7 to evaluate the limits as x goes to 2 of my variable x, and I can use property 8 to look at the limit as x goes to 2 of 9. I think I said those backwards, but 7 was our constant and 8 was our linear function. So here, this means I can actually evaluate. This is going to be 4 times 2 squared, 7 times 2, and then again, for our constant function, remember that's just whatever the constant is. Okay. And then from there, notice my limits are gone. I've now evaluated the limits. I just need to finish evaluating the terms I got here. So now we're going to just multiply through. So it looks like a 16 minus a 14 plus 9. And when we add those together, there's our limit. So let's look at another one. Let's look at the limit as x goes to 3 of x squared plus x plus 2 divided by x plus 1. Okay. So here again, we're going to do the same thing. In this case, I'm actually going to start with property 5 because I have a fraction inside of my limit, so I want to change it to a division. So we're going to take the limit as x goes to 3 of x squared plus x plus 2 divided by the limit as x goes to 3 of x plus 1. Okay? And again, this is our property 5. Okay? From there, we're doing a lot like what we did with the polynomials. So from there, we can take and separate out all of the additions into individual limits. And again, this was property 1. Now we can again rewrite the squares, and we can go ahead and use our constant and linear properties. Okay, so from here I can go ahead and make this a 3 squared plus 3 plus 2 over a 3 plus 1. And again, this comes from properties 6, 7, and 8. And now, again, we've gotten rid of our limits, so now it's just a matter of evaluating. So I can go ahead and simplify on the top, and then on the bottom, and of course, make sure you reduce for your answer. In this next example, we want to look at the limit as x goes to pi, as x cosine of x. And unlike the last ones, we're not going to write out every single step. We're still going to evaluate the limit using the limit laws, but you don't always have to write out every detailed step and list out the properties, okay? Unless you're asked to. So here, if I want to look at this limit, the first thing I notice is it's a product. So I can basically take the limit of the first times the limit of the second. From here we know limit as x goes to pi of x is just going to be pi. And again, that's because we're just looking at evaluating that linear function. And then for cosine of x, this is basically our limit as x goes to a of f of x, which means I can just plug in as long as it's defined or the limit exists. And so here, that just means I'm looking at a cosine of pi. So now simplifying, we see that we're just going to get negative pi. In the next example, we're looking at the limit as x goes to negative 1 of x e to the negative x. And so here again, we're going to use a couple of those properties. Just like in the last example, we've got a product of two, so I can think of separating these. Okay. And again, the first, I can go ahead and evaluate. We can see that's just going to be a negative 1. And here again, even though I'm now looking at x in the exponent, again I can think of this as my f of x. Okay? So if this is my f of x, the limit is just going to be the f of whatever my a value is. So this is going to be e to the negative of negative 1. And now if we simplify this expression, we can see that this is just going to be negative e. And lastly, if we look at our tangent x over x squared plus 1 and the limit as x goes to 0 of that, we can do again the same type of thing. I can separate it out to the top and the bottom. And use my properties to evaluate. On the bottom, again, we're back to a polynomial. So I can think 0 squared plus 1. And on the top, again, I can think of that as my f of x. Okay. And then from there, again, we can simplify, and we see that we get a value of 0. So the last few examples, we used our limit laws to show that we can directly solve for our limit of a function. But in some cases, you may not be able to directly solve. You can still use those limit laws, but you may have to do some algebraic manipulation first. And so here is one of the properties that's going to be useful in making that happen. If I have two functions, f and g, where they are equivalent everywhere but one point, so let's call it x equals a, then what we can see is that the limits are going to be exactly the same everywhere except at that, even at that point. Okay? So basically what we're looking at here is if I have two functions, I'm going to call this one f of x, and g of x, I'm going to call the orange function. It's exactly the same at f, except we have one point where maybe the limit, the value is something different. And everywhere else, it's the same function. Okay? So here, basically what it's saying is if I look at the limit at this point a, the limits are going to be equivalent. And that's true because if you remember what we said way back in the beginning of the limit video, it's what the values are approaching, not what they equal. So as I come in from the left, regardless if I'm looking at f or g, I'm approaching the point here. And if I come in from the right, I'm still approaching the point here. So even though they differ at that single point, because they're the same everywhere else, the limits are going to be equivalent at that point. So this is useful to us because some of the functions that we're going to have the limit laws don't apply directly at first, and like I said, we have to algebraically manipulate them before we can use the laws. So an example of this is the limit as x approaches 1 of x cubed minus 1 over x minus 1. Okay? And first you need to convince yourself that the limit law doesn't work here. And primarily what the problem is if I try to evaluate these polynomials like we did with the limit laws, what I find is that when I plug in 1, I'm basically going to get a 0 over 0. Okay, so something that's not determinable. Okay? If you get something that's not determined or something that's undefined, then you have to use some algebraic manipulation to get your limit. And again, it's basically what this is saying. It says I can rewrite the function and simplify it down to something equivalent that may exist everywhere, and so then I can find the limit. Okay? And so here what we're going to do is I'm going to start, there's not much I can do except to factor. So we're going to rewrite this function by factoring the top using our difference of cubes. And then the first thing we notice is we can cancel some terms. Okay, so we'll cancel those x minus 1s. Now we're back to a polynomial function instead of a rational function, and we notice if I plug in 1, I am no longer getting something that's undefined. Now one of the things you have to be careful of is, again, if the functions are equivalent except at that one point, it means I can't really write equals without the limit here. Because as we can check, x squared plus x plus 1 is not the same as x cubed minus 1 over x minus 1. And we can clearly see that because one of them is evaluable, can be evaluated at 1, whereas the other one can't. Okay? So you really do need the limit there to make sure it's a true statement, and so that it makes it something that can be evaluated. Okay? Another example of this would be looking at the limit as x approaches 0, the square root of x plus 1 minus 1, all over x. Okay? Similar type of thing, just a different type of function. So here again, the first thing to notice is, again, if I try to evaluate, if I plug in 0, I get a 1 minus 1, which is going to be 0. On the bottom here, if I plug in, I get 0. And so again, it's something that can't be determined. So again, it means I can't plug in using my limit laws directly. So here again, we need to rewrite. So for this one, if I look, the limit as x goes to 0 of that function, again, the only way I'm going to be able to kind of simplify that function is, in this case, using the fact that there's a radical here. And so what we can do is we can multiply the top and the bottom by the conjugate so that we can get rid of the root. So when we multiply out, those roots will disappear. Well, they don't disappear, they go away when we multiply it out. We do get a root in the bottom, but we'll see later that's not going to be as much of an issue. Okay, so up top I can simplify. I'm basically going to end up with just x. The x over the x will cancel out. And now when we try to plug in using our limit laws, again, the square root will take the limit of the inside, so 0 plus 1, square root of that, plus the 1 gives us a 1/2. Now in some cases we're going to have where the limit laws by themselves and the algebraic manipulation included are still not enough to evaluate the limit. And so in those cases what we're going to need is to be able to kind of use the fact that there are one-sided limits in order to evaluate the limit. So here's an example of something like that. If we look at the limit as x goes to negative 6 of 2x plus 12 over the absolute value of x plus 6. Okay. So again, the first thing we want to notice is if I try to plug in directly, we get a problem. So again here, if I plug in directly, I can see if I put in a negative 6 on the top, I get a 0. If I put in a negative 6 on the bottom, I get a 0. That's not good. That can't be determined. So we'd have to use either algebraic manipulation or something else. Now the problem here with algebraic manipulation is there's not really anything I can do. It's not a radical, so I can't use the conjugate to get rid of anything. It doesn't really factor and simplify. I mean, I can pull out a 2 and I'm going to get an x plus 6, but that doesn't cancel with the absolute value. And so the methods that we would normally use to simplify this don't work on this function. So here, another thought is to use the one-sided limits. And what that means is I'm going to look at the limit as x goes to negative 6 from the negative side of our function. And then I'm going to look at the limit as x goes to negative 6 from the positive side of the function. So in this case, if I'm looking from the negative side, first off, I'm already at negative 6 and I'm looking further negative than that. So it means all of my x values are negative. Well, if all the values here are negative, if I put in something like negative 7, negative 8, negative 100, all of the values on the top are going to be negative. And it doesn't matter what I put in here, whether it's positive or negative, the absolute value will be that value, meaning an x plus 6. And again, because I'm changing my function sum, I need to consider the fact that I can't drop my limit yet. Okay? But now if I look at this, based on knowing those values are negative, I can factor out and simplify. So here I can pull that 2 out. And we can see that now I can simplify, because the x plus 6's will cancel. And when I take the limit of the constant, we just get that constant. Okay. Now again, we're not done. That's not the limit. That's only the one-sided limit. And again, we're looking for the two-sided limit. So now we need to look at the other side. So if we consider the limit as x goes to negative 6 from the positive side of our function, we can do the same thing. But now if I'm at negative 6 and I'm coming from the positive side, notice anything bigger than negative 6 means the top is going to be a positive value. And again, any number I plug in there, when I take the absolute value, I'm still just going to get an x plus 6. Again, we need the limit to make things equivalent, and then from there I can simplify. So we'll cancel out the x plus 6's. And then the limit of our constant is going to be 2. So now, if we go back to what we're trying to find, we want the two-sided limit. But remember, the two-sided limit is only exists if both of the one-sided limits exist and are equivalent to each other. And so here on the left, we got that it's negative 2, and on the right, we got it's positive 2, which means our two-sided limit as x goes to -6 of this function does not exist. Okay. And so, like I said, some cases you're not going to be able to use the algebraic manipulation or the limit laws directly. You may, in some cases, have to use the one-sided limits to determine what the two-sided limit is doing. Now, in other cases, it is readily apparent that you're going to need to use one-sided limits. So unlike the last example where I'm looking at just a regular function, in the case of piecewise functions, it's a little more clear that you have to use one-sided limits in some places. So here, if I look at f of x equaling the square root of x minus 5 for when x is greater than 5, and 10 minus 2x for x less than or equal to 5, then if I want to find the limit of x goes to 5, I've got to consider the fact that both sides may be doing different things. Okay? And so here, again, I'm going to need one-sided limits. So if I look at the limit as x goes to 5 from the negative side of f of x, well, for a piecewise function, it's kind of defined for me since it's breaking at that point. So for less than 5, or the negative side of 5, I'm looking at the bottom piece of the function. So this means I'm looking at the limit as x goes to 5 of 10 minus 2x. Okay? Notice here I dropped the negative side, or from the left. And that's because once I've plugged in which piece of the function, in this case, I don't need the negative anymore, because if I'm looking at this piece, it is already determined that I'm to the left of 5. Okay? So here we can simplify. This one's a polynomial, so I don't need any algebraic manipulation. Plugging in, I can see I'm going to get 10 minus 2 times 5, or 10 minus 10, which is 0. For the other side of the function, so now we're looking at coming in from the positive side. Same thing, I can start by looking at that top part of the function, so the square root of x minus 5. And again, I can drop the positive because now I'm on the positive side of 5, and it's defined in our function that way. Here again, when I go to simplify, this one is a root of an f of x, so I can take the root of the limit. The limit of x minus 5 as x goes to 5 is going to be 5 minus 5, or again, square root of that is 0. And so here, this tells us the limit as x goes to 5 of f of x is equal to 0 when f of x is equal to our piecewise function, square root of x minus 5 and 10 minus 2x for x greater than 5 and x less than or equal to 5, respectively.